66 million years ago, something hit Earth so hard, it ended the age of dinosaurs. We've known that for decades. But here's the thing scientists still couldn't agree on. What was that object actually made of? Where did it come from? And what part of the impact actually did the killing? A new, not yet peer-reviewed analysis says it may have found a chemical fingerprint that answers at least one of those questions. And the answer is stranger than anyone expected. Researchers looked at the thin layer of clay found all over the planet, right at the boundary between the age of dinosaurs and the age of mammals. That layer is packed with material from the impact itself. By analyzing rare trace elements in that clay, including isotopes of a metal called ruthenium, the team argues the impactor was a very specific and unusual type of space rock called a cochondrite, a category of carbon-rich meteorite that is extremely rare among the debris we normally find on Earth. If confirmed, that would mean the object came from a distant, unusual part of the solar system, not the more common asteroid population we typically blame for impacts like this. The study also suggests something else, that the fine dust thrown into the atmosphere by the impact, not sulfur released from the rock at the crater site, may have been the main reason the planet went dark and cold afterward. To understand why this is hard, picture being handed a single ash flake from a house fire and being asked to describe down to the manufacturer exactly what kind of couch burned. That's roughly the challenge here. The asteroid itself vaporized completely on impact. There is no chunk of it sitting in a museum. All we have is a razor-thin smear of debris spread across the entire globe, mixed in with ordinary Earth rock, and aged 66 million years. Scientists have to tease out incredibly faint chemical signatures, ratios of rare elements that barely exist in normal rock, to guess at the original object's identity. It's a bit like forensic fingerprinting, except the fingerprint is a whisper, and the crime scene is the whole planet. As for the two suspects for what actually killed most life on Earth, one camp has long argued that the impact site itself, which was rich in sulfur-bearing rock, blasted so much sulfur into the sky that it formed sun-blocking aerosols. The other camp argues it was simply the fine dust and debris, kicked up by the sheer violence of the blast, that plunged the planet into darkness and cold for years. This new study tips its hat toward the dust theory, but it does not settle the argument. This might sound like a historical footnote, but it connects to something much bigger: how we predict and prepare for future planetary disasters, whether from asteroids or from human-caused climate shocks. If dust, not sulfur, was the dominant killer, that changes the models scientists use to estimate how much material an impact needs to eject, and how long, to trigger a global cooling event severe enough to collapse food chains. Those same models inform how seriously we take asteroid defense today, and they even echo uncomfortably some of the science behind nuclear winter scenarios. Getting the mechanism right isn't just trivia about dinosaurs. It's about correctly understanding one of the only real-world case studies we have for how the sky itself can end an ecosystem. It's important to be honest about where this stands. This finding comes from a preliminary report that has not yet gone through peer review, and the scientists themselves describe their conclusion as likely, not certain. Other researchers have proposed different compositions for the impactor entirely, and the sulfur versus dust debate has been argued for years without a clear winner. What happens next is more sampling, more isotope analysis from boundary layer sites around the world, and independent teams trying to reproduce these results before anyone can call this settled. If it does hold up, we'd have a much more precise origin story for the rock that ended the dinosaurs, and stronger evidence for exactly how it killed. If it doesn't, it joins a long list of clues that got us closer without giving us the full answer. So, do we finally know exactly what killed the dinosaurs? Not quite. What we have is a compelling new clue. A whisper of ancient chemistry pulled from a layer of clay thinner than a business card, hinting that a rare visitor from a distant part of the solar system, and the cloud of dust it kicked up, may have plunged our planet into darkness. It's not the final answer, but it's a reminder that even the most famous extinction event in history still has secrets left to give up, 66 million years later.